Okay, we should be live right now. Just wait for a second. Perfect. So we are live, and let's start the lecture 13, which will be the complementary lecture for finishing the differential geometry. So briefly, I will review what we have done during the last lecture, which was the exterior product, or exterior algebra, or what we call it Grassmann algebra. And if you recall, we say that here in the definition that we have, we deal with differentials, but we are treating the differentials in a completely different way. So we call it an operator. We are very careful how these operators are acting differently, and how they are. You can, for example, you can sort them out in a certain formalism. So if you remember, we say that you may have just what we call it normal function or standard function of f, and this standard function of f does not contain any differential. Then we call it zero form. Okay. However, you may take the differential, and what you will end up, it may be something like this. It will be ax of a function of x, y, and z. Remember that we generalize this also for n-dimensional space, and that was the beauty of using the exterior algebra. And we have a dx plus ay x, y, z dz, the dy plus az x, y, z dz, or in general way, we call it a1, which can be function of x1 until, I don't know, xp, dx1 plus a2 x1 xp dx2, and until you have ap of x1 xp dxp. We call these one form. Okay. Why we call it one form? Because only one derivative or one of the differentials exist there. Then we may have different things like b, which we call, by the way, we call them omega. We can have a different form which has b1 of x1 until xp, and then you have the dx1 dx2 plus b2 of x1 xp dx1 dx3, and until you will have how many elements do we have? So we have the choice of 2 from P. So the choice of 2 from P. So it's a P factorial divided by 2 factorial P minus 2. Okay, factorial. So that will be P times P minus 1 divided by 2. So that should be, I don't know, P minus 1 divided by 2, and then we have dx p minus 1 dxp. Okay, and we call these the two forms. And of course, we can label it with omega, but remember why we call it two forms, because we have these kind of terms, which two differentials are appearing in the calculation. And remember, these differentials that appears, they are different. So we don't have any for example, dx1 exterior product, or what we call it the wedge product of dx1. So this is equal to 0, as we describe it later on, and we will see. I mean, we proved that in the last lecture, during the last lecture. And in the same fashion, you can build up in this, let's say, p dimension or d dimension, you can build up what we call it the p form. So for this explicit case of the dimension p, we can build up the p form, which can be any function of, let's call it h, of x1 until xp. Then we have dx1, dx2, dx3, until you will get dxp. This is in dimension p. So we say that in dimension p, there will be p plus 1 form of a differential form, essentially, which is 0 form, 1 form, 2 form until the p. So the sum of all of them will be p plus 1 form. And if you recall these, what are the property of these wedge products? This was the wedge product. And we say that, well, the wedge product is very important and really powerful tool, because you can define it and determine it in n-dimensional space. And you will see that today during the lecture, that is very powerful, that simplifies many calculation in a very, very simple and compact formalism. Okay, so what are the exterior derivatives? Let me just review a few of those examples that we added during the last lecture. So so what was the features of them, if we want to discuss? So there were a few features that we pay attention to. Okay, so these few features, they were like this. So the first one, which is very, very important, is that if you have a dx, wedge product of dy, this is equal to minus dy dx. So it's antisymmetry. So whenever you swap the two differentials, you have to end up with a negative sign. This negative sign is the feature of that. Okay. So from these, we say that, of course, I can use this one, and I can do dx wedge product of dx. That will be equal to, I can swap them together, then I will get minus sign, and then I will get dx cross dx. And the result of these will be minus dx wedge product of dx. So you will see a quantity like this, which is equal to minus quantity. So therefore, immediately I will get the result that dx wedge product of dx must be equal to 0. Okay. This is the first property that we were dealing with, and we discussed that last time. On the other side, what we knew that if you take the two, let's say omega-1 wedge product of omega-2, then clearly you can swap them together. You will get minus omega-2 omega-1. Okay, so omega-1 and omega-2, they are, let's say, p forms. And on the other side also, you have the associativity relationship, which is omega-1 omega-2 wedge product of omega-3. Then the result of these will be omega-1 omega-2 wedge product of omega-3. So it is not important as far as you keep the sequence of omega-1 omega-2 and omega-3. It is not important where do you do the wedge product. Do you do it first with omega-2 omega-3, or you will do it with omega-1 omega-2? But however, if you swap any locations of these two, for example, if you swap the first two together, you will get minus omega-2 omega-1. Then the result of these will be omega-2 wedge product of omega 1, omega 3. So when you swap them, then you have to expect the sign will change. If you have any function of, or we call it the zero form, okay, this is the zero form, is not differential form, is a zero form of omega 1 wedge product of omega 2, then you can cast it like a omega 1 wedge product of omega 2, or you can cast it in the last term, so you can write it as omega 1 wedge product of a omega 2. So if you have any zero form, you can easily move the zero form to the front, so it's not a big deal. So if you have a specific function, you can just take it to the beginning, or you can move it around without having any trouble. And the other property that we discussed about that was omega 1 plus b omega 2 wedge product of omega 3, then easily we say that that will be a omega 1 wedge product of omega 3 plus plus b omega 2 wedge product of omega 3. So you can expand it on the right side, and the same situation also will happen on the left side. When you swap these two together, indeed you will get minus omega 3 wedge product of a omega 1 plus b omega 2. So indeed the result of these will be identical, so you will get a minus a omega 3 omega 1 minus b omega 3 omega 2. Okay, so that's the expansion on the right side. On the left side also the same situation. And remember, when you have one form differential, for example, you have a dx1 is one of the forms, and the other one is b dx2, then essentially the wedge product of dx1 b dx2 will be equal. Since these two, they are the zero forms, you can take them out, so you will get ab dx1 wedge product of the dx2. So from the 2 1 forms, you will get 1 2 forms. Okay, so which is very important. And what also we discuss and we say that is important is the Levi-Civita notation. And we say the Levi-Civita notation that we introduced in the last time was in the 3-dimensional space of x, y, and z, and we call it dx1, dx2, dx3, and then we call it epsilon 1, 2, and 3, and we call these, or you can go in a general form as epsilon I, j, k, and then you have a dxi, wedge product of dxj, wedge product of dxk. So we call these Levi-Civita notation, and we say that when I, j, and k, they are in a positive permutation, you will get a +1 sign. So indeed, if you write it in this way, epsilon 1, 2, and 3 will be equal to 1. But however, if you swap them in any fashion that you want, you have to go with exterior algebra formalism. For example, you can write epsilon 1, 2, and 3 dx1, dx2, dx3. Now I can take also these and I will swap them. So I can write it as a dx2, dx1, and dx3. And since I swap the first two, then I have to go with a minus sign. So then immediately I will get the result that epsilon 1, 2, 3 is equal to 1, but epsilon 2, 1, 3 is equal to -1. If you swap them another time, then you will get dx2, dx3, and dx1. I'm swapping these two together. then I will get another minus sign. It will be minus sign power of 2, which is a positive sign. Then that is equal to epsilon 2, 3, 1, which is equal to plus 1. And using the same formalism, you can expand and get Civita notation in n-dimensional space or in p-dimensional space. So you can go with epsilon of let's say I, j, k until the p, and dxi, dxj, dk, xk, H product of the dxp. And then as far as I is smaller than j, is smaller than k, is smaller than p, and of course that should be equal to 1, then this notation epsilon ijk is equal to 1. But whenever you swap the two of them together, you will get a negative sign. So for example, epsilon ji, k, and p, that will be equal to -1. So remember that in that specific case, you have to pay attention on how these exterior products are written, okay? So this is the way that you can build up the Levi-Civita notation in a higher dimension. And on the other side also, what we have introduced, we introduced the Hodge operator, and we call it also the complementary differential form. Complementary differential form, or we say that that's a dual operator. If you recall, we say that if you have any omega, or let's say omega, then we can define an operator which will give you the conjugate of this, or the dual space of that, and we show it with the star of omega. And what is the star of omega? The star of omega and omega, they should complete the space. They should complete the space in dimension, in the desired dimension of, I think was p, if we consider in the past. Okay, so and we made a few examples. We say that, for example, if you consider the three-dimensional space, the Euclidean space of x, y, and z, then what we can get the zero form for sure, which will be some specific function of f of x and y and z. This is the zero form, and let's call it this the differential form. And then the dual space of this will be the star of f, which essentially we showed it with dx, dy, and dz. We say that if you look at the entire space is a three-dimensional space. You will have zero form, you have one form, two form, and three forms. So in order to have all differentials, since here in the zero form you have no differential, then you have to have the dx, dy, dz, all of them together, and the sequence should be in the positive permutation that we had. So, and then we consider that what is happening when you have one form, and this one form can be, for example, dx. If it's a dx, then the star of dx will be equal to dy, dz. Okay, and if it's dy, then the star of dy will be equal to dz, dx. If it's the dz, then the star of dz will be equal to dx, dy. These are the dual space, or the dual operator that we define and we determine during last lecture. And in the same way, you can get the two form. And the two forms, for example, you can have dx dy, and definitely the star of dx dy will be the other differential, because they should complete the space. So it will be the dz. So the positive circuitation permutation also is very important. If you have dy dz, the star of dy dz is equal to dx. The star of z dx, the star of dz dx will be equal to dz. Sorry, dy. Okay, so so the one form, the dual of one form will be the two forms. The dual of two forms will be one form. Remember, this is the Euclidean space, and the Euclidean space, usually the metric is 1, 1, 1. That's the reason that I have not considered the action of the metric. So this is the way that people, they can write it in a proper way. So let's do a little bit of, I think we stop here because we introduced the dual and the what we call the Hodge operator or the star operator, which is going to the dual space or the complementary space. And I think we stop here. So now let's consider that I have two, and I think I made an example as well, if I'm not mistaken. But now let's go with some general solutions or general problems that we want to tackle. So assuming that we have two one-form differentials, so is, for example, a x of x, y, and z dx plus a y of x, y, and z dz, dy plus az of x, y, and z of dz. And then we have another one form, which is a bx of x, y, and z of dx plus by of x, y, and z of dy plus az of x, y, and z of dz. Remember, I can, for simplicity, I can omit also the functionality of x, y, and z, but we know that in this Euclidean space, that should be the functionality. Okay? Any questions so far? Or we are okay? No questions?
We have one question in the chat. Yeah. So it says, what is exactly the geometrical interpretation of dx, dy, dz on a three-dimensional manifold? For example, dx, dy, dz is an element of volume.
Yeah, indeed. So we will right now we are tackling this problem. Okay. Good, lovely. So just remember that sometimes I'm not writing the functionality, and this functionality, they are not important for me so far, and I will keep it in this way. Okay. So now I'm asking you what is going on with A, which product of B. So I have to take the AX dx plus AY dy plus AZ dz. Remember, now it is very important to keep the orders. Which product of bx dx, by dy, bz dz. So let's do the wedge product. It will be ax. Remember, these are ax, ay, az, bx, by, bz. They are the zero form, so the standard function or normal functions that we are dealing with. So easily you can move it around, but I cannot do this with dx, dy, dz, because they are the differential forms, so they are the one form, and I cannot move them around easily. Okay. Or I have to be careful when I'm doing that. So the first term will be ax, bx, dx, dx, ax, by, dx, dy. AZ, AX, BZ, DX, DZ, AY, BX, DY, DX, AZ, AY, BY, DY, DY, AY, BZ, DY, DZ, AZ, BX, DZ, DX, AZ, BY, DZ, DY, AZ, BZ, DZ, DZ. So what is the result of DZ, DZ, DY, DY, DX, DX? As we discussed, the wedge product will be 0, right? So what we care is usually going with the positive orders, or let's say X, Y, Z in sequence. So then I will cast it in such a way that X, Y, and Z also, they will show up in the wedge product in the proper way. So this is the dx dy. So it means that is xy. So it's a positive. I will keep it like that. This is xz. Xz is going negative sign. So I will write it as minus dz dx. Okay. This one dy dx is going in a negative way again. Is going from this way. So I will write it as minus dx wedge product of dy. Dy dz, that term is positive, is the same way because it's going yz. This one x zx is going again in a positive way. I will keep it like this one. And the last term is dz dy is going zy in a negative way. So I will write it minus dy dz. So I will cast them together. I will put them in a proper way. So this term will go with this term. So it will be, let me write it in a proper way. It will be sorry, not going with this term, by the way. My apologies. It goes with this one. Goes with this one. So it will be AY BZ minus AZ BY DY DZ. That's this term and this term. Then I have another term, which is, sorry, plus the other term, which it should be, it should be this one. It should be this, and that term. It will be AZ BX minus AX BZ DZ dx. And finally, the last term, which will be, sorry, will be this one and that one. That will be AX BY minus AY BX dx dy. Okay. So the wedge product of A B now is given by AY BZ minus AZ BY dy dz plus AZ BX minus AX BZ dz dx plus AX BY minus AY BX of dx dy. Now let me ask you a question. What is happening with the star operator of A wedge product of B? So what I have to do, I have to look at the dual of these. So what I have to do with the dual means that dy dx, dy dz, dz dx, and dx dy, they have to replace based on these rules that I have written here, or these rules that I have written here. So dxy dy, dz dx will be replaced by dy. Dy dz will be replaced by dx, and this one will be replaced by dz, and the zero forms, they will not be affected because the zero forms, they are look like the no standard functions, so they are not the differential form. So the star of these will be ay bz minus az by plus az bx minus ay bz. Then I have ax by minus ay bx. So what's that, guys? So Isa said that is okay. Yes. Can we define it as a determinant? Well, yes, indeed, you can write it as a determinant, but I will say that they are look like the components of cross product of two vectors in three-dimensional space. Because this is that the star A cross B is look like A cross B, the x component of dx, A cross B, let's write it as a vector just to give you something to remember, of y dy plus A cross B of z dz. Okay, so this is the beauty of differential geometry, which is essentially allowing you to get let's say the cross product even in that specific form. So in a similar fashion, you can write it in n-dimensional space. In n-dimensional space, you can determine the cross product in a certain way, but you have to be very careful with the calculation. And here you will see that clearly the cross product that we have it in a three-dimensional space, it shows up in this specific fashion. Okay, any questions so far?
No, we have no any question.
Okay, lovely. Good. So that was about the A cross B. And now I'm asking you, what is happening with A, not only A, wedge product of B, but also wedge product of the C, which is all of them, A, B, and C, they are one form. Okay? So it means that I have AX dx, AY dy, AZ dz, wedge product of BX dx, BY dy, BZ dz, and then I have a wedge product with C, which is CX dx, CY dy, CZ dz. Okay, so we have already done the first term. Okay, so the result of these two, we just did the calculation. It is A y b z minus A z by dy dz. Are you following, guys? Yes or no?
Yes.
Okay, I'm just writing down what we have just obtained plus az bx. Good, thank you. Minus ax bz dz, which product of dx plus ax by minus ay bx dx which dy. Okay, and now the entire of these should be which product. Remember, I have a which product here with c, which is cx dx cy dy cz dz. Okay, so now I'm asking you a question. Can you just write it for me? Okay, it's a little bit awkward, but I'm going with something different. What is happening with is one term, two terms, three terms, which you have to multiply it by this one, and that one. So in general, how many terms I'm expecting? I'm expecting 9 terms because it would be 3 multiplied by 3. But let's go in a sequence. So what is happening with the first term multiplied by the first term? So it will be the two zero forms, which is the AYBZ minus AZBY and CX, they will be multiplied together. So that will be AYBZ minus AZBY, and then you have a CX. Then what is what you will get from the product of the two forms, which is here, and this one form that we have it here? Do we get 0? Why do we get 0? Because the term that I have is dy, which product of dz, which product of dx. Is it 0? Oh yeah, okay, it's not 0. Okay, so this is the 3 form that I'm expecting. From the 2-1 form, you will get 2 forms, and from the 2 form multiplied by 1 form, you will get the 3 form, and this is the 3 form that we got. Now let's look at the, I'm highlighting it with blue. So the first term multiplied by the second term, what you will get? First term multiplied by the second term. Again, we will get the 0 forms, which is the AYBZ minus AZBY, and then CY. But then we get another term, which this term, whatever is that, is a CY. We get dy, which product of dz, which product of dy. What is the result of this? Mobin says 0, Isa says that is 0. Do you agree, guys? Because the 2 of the differentials are repeated. So I can easily write that as a dy, which product of dz, which product of dy. I will write it in this way. I will write as a minus sign, dy. Then I will swap these two, and I will add a minus sign here. Then I will get the dy dz. Using the associativity, I can keep them these together, and dy is 0. So the result of this will be 0. So the result of anything that is the differentials are repeated over will be equal to 0. So then also the third term will be 0 because z is repeated. So if I want to simplify A cross A, which product of B, which product of C, I will only get these terms. It will be the first one that I have written here, it will be, the result of this will be AY BZ minus AZ BY of CX. Then I have a DY wedge DZ wedge DX. Then the second term also I have it, so it will be plus AZ BX minus AX BZ of DZ which DX which DY. And finally the last term, only the exactly, Isa, you are completely right, only 3 terms will remain, and the last one will be AX BY minus AY BX, and then the final term is DX which DY which DZ. Okay, so let's cook it now, because we know that only in the 3-dimensional space, how many 3 forms do we have? Only 1 3 form do we have. Okay, so we have to write it as a positive sequence or positive permutation of X, Y, and Z. So what I have to write down, so these can be written as the first 2 swap together, that will be DX, okay, which DY, which DZ with a negative sign, DY. Then I will swap these 2 together. I will get minus, in others minus DX, which DY, which DZ. So I got what I wanted. So it's identical to this. This one is, I will swap these 2 together. I will get minus sign. I will get minus DX, which DZ, which DY. And then I will swap these 2 together. I will get plus sign, DX, which DY, which DZ. And the last one is already positive, so it's DX, DY, DZ. So if you write all of them together, you will get only one term, which is AY BZ minus AZ BY of CX plus AZ BX minus AX BZ. And then there was another term here. Oh, I have forgotten that. My apologies. That should be CY. And here there should be a CZ. And then I have a CY plus AX BY minus AY BX of CZ. Okay. And then I have a DX, which DY, which DZ. Oh, yes. Thank you, Omid. I haven't seen your, and Mobin, I haven't seen your comment. So, well, beautiful. So this is the product of the T1 form of A, wedge, B, wedge, C, which is identical, by the way, to A wedge. This is identical to this one. Okay. Well, beautiful. So the product of the T1 forms will be the T form. Now, what is happening with the dual of this? So the star, applying the star operator to A wedge, B wedge, C. So this is the 3 form. What is the conjugate of the 3 form? Can you type in the 3-dimensional space? Yes, exactly, is 1. So the result of this will be equal to AY BZ minus AZ BY CX and plus the other term. And then finally what you have 1, because that's the 0 form essentially, which is 1. And if you simplify these together, this is nothing more than AX AY AZ, and this BX BY BZ, and this is Cx, Cy, Cz. What's that? Is if you expand this, it look like this determinant of the matrix of 3 by 3, and this is nothing more than A dot B cross C. Okay, so the three forms, essentially the three forms of A, B, and C, the wedge product of them, will, if you look at the dual space of that, will is identical to finding a volume which is created by the three vectors of A, B, and C. So this was your question, which you asked during the lecture. Okay, so that's really the differential formalism. Good. Any question? Are we good so far?
Thank you.
No
We have
questions so
not
far.
any question.
Okay. If there is no question, then let's go for it. Okay, all good. Now, so far, I will encourage you, by the way, I'll really encourage you to look at these basic calculation, because you look like arithmetic, which we learn in the school, in the primary school when we were kids. So this is a new definition, is entirely new definition that you have to get familiar. So I will encourage you really to do, it's a really simple mathematics with this kind of algebra, because it is very important to get familiar with the concept. And remember that what I have done in terms of finding the dual space or the dual operator, it was for the Euclidean three-dimensional space. When you have a metric, and this metric is not only given by 1, 1, 1, but is given by, for example, some specific pattern, then you have to take care of the sign as well, okay? Or you have to write it in the proper formalism. So let me just give you one example, because I don't want you to get confused before going to the differential calculations. Is the metric of, I think I've written somewhere, yes, is the metric of the Minkowski space, okay? Which people, or we use it in special relativity. So in the Minkowski space, we have 4 coordinates, okay? These 4 coordinates are given by time, okay? Well, oops, page which. So this is given by, usually we call it the 0 coordinate, which is CT. And then we have x1, which is x. We have x2, which is y. And we have x3, which is equal to z. Okay, you can write it in any other metrics that you wish, is up to you. The curvilinear coordinate that we learned properly in the past. Okay, so if you write it in this way, there is the metric of this space can be given by g mu nu, will be given by 1 minus 1 minus 1 minus 1. Okay, this is the metric that I have. It. Some people, they write x0 as a ICT, okay? If you write it in this way, that's a different scenario. I'm not talking about that definition. But remember, it's very important when you do the calculation, you have to restrict yourself to one specific notation. You are not allowed to change the notation, okay? I think we always use this metric. We have not used the others. We have, and sometimes also I like to do this kind of assumption of going with the dimensionless coordinate. And what I will do in this dimensionless coordinate, I will take h bar equal to 1, and also I will take c equal to 1, okay, as well as epsilon and mu is a notation. always you can recover the factors, you can recover the scale. If you write it in this way, the 4 coordinates that we discussed, which is x0, x1, and x2, and x3, and others, what we call x mu, will be given by t, x, y, and z. Okay, and still the metric is the same. G mu nu is given by 1, minus 1, minus 1, minus 1. Exactly, it's natural units. Yeah, thank you. We use it a lot in GR. Okay, so far so good, right? Now remember how many what is the dimensionality of my space? So now I have the dimension is 3 dimension. One is the coordinate of t, one is the coordinate of x, one is the coordinate of y, one is the coordinate of z. So essentially associated to them, what I have the differential of dt, I have a differential of dx, I have a differential of dy, I have a differential of dz. Good. So I have these differentials. So essentially, the 0 form will be any function of t, x, y, and z. This is the 0 form in this space. 1 form, anything that is built up with dt, dx, dy, and dz, any linear combination of them. So you can write it as, I don't know, a0 dt, a1 dx, a2 dy, a3 dz. So the general form for 1 form will be this. So it will be a1 dt, a0 dt, a1 dx, a2 dy, and a3 dz. Okay, that's the 1 form. Now the question is that what are the 2 forms? How many 2 forms do we have? So we may have dt, wedge product of dx. We may have dt, wedge product of dy. We may have a dt, wedge product of dz. Then also we may have dx, wedge product of dy. Remember, pay attention to the way that I am writing this. Okay, we have dx, wedge product of dz. And also I have dy, wedge product of dz. So those are the 3, let's say the 6 2 forms that I have. So any linear combination of that will be also a 2 form in that specific coordinate. How many 3 forms do I have? I can have dt, wedge product of dx, dy, or I can have dt, wedge product of dy, dz, or I can have a dt, wedge product of dx, dz. There is another one, which is dx, wedge product of dy, wedge product of dz. Exactly, I have 4 of them. Lovely. So these are the 3 forms. What about 4 form? And that's the final one, by the way. Only one, which is dt, dx, dy, and dz. Only I have 1 4 form. Lovely, Isa and Mobin, thank you. Now the question is that, guys, what is happening with the dual of them? What is happening with the star operator or a Hodge operator of this space? So let's go and let me introduce this. Here the metric also plays role, and the metric is really important. Okay, so remember the metric that we had was 1 minus 1 minus 1 minus 1. So remember that X, Y, and Z in the metric, they have a negative sign. The determinant of the space is -1. So these are really important concept. So then let's go with the first one. So what is happening with the zero form, which is, they say this is the differential form, and that's the star of the differential form. So let's write it in this way. If you have omega, that's the star of omega. So for example, your omega is 1, okay, is a zero form. What is the dual of the zero form? Is a 4-dimensional space. I have 0 form, 1 form, 2 forms, 3 forms, and 4 forms. So what are missing in the 0 form? The 4 forms, exactly. You will get the 4 forms, but as a sequence. Remember, the sequence should be dt, dx, dy, and dz. Okay? The metric, remember, here is 1. The metric on the other side is -1. It's really important to pay attention. Okay? Good. Now, look at the other one. I'm telling you what is happening with the dt, dx. By the way, this is the star of 1, which is equal to that. d1, dz. What is the star of dt, dx, dy, dz? I want to see the result from you guys. Can you tell me what is the result of this? Are you sure? You have neglected the metric. Here, the metric is -1 and is not appearing on the other side. So the result of this is -1. That's the trick that I told you, that you have to be very careful. Shania, yes, you are correct. So it's -1 because we have to pay attention to the metric as well. If the metric of the space, assuming that I have a space and the metric was 1, 1, 1, 1, then that was equal to 1 and had no problem at all. Okay? So, and now let's go with another example. Let's say for, I will go with the 3 forms because the 3 forms are important as well. So let's go with the dt, dx, dy. This is one of the 3 forms. Okay. What is the star of dt, dx, dy? Y minus. Remember, here you have a minus, okay, which is plus. Why you are expecting the minus dz? So for the 1 form, okay, remember, let's go from this one. I'm repeating that. So the 1 form that I have, sorry, the 0 form that I had, and my question was, what is happening? What is happening with the dual of this? The dual of 0 form. The dual of 0 form will be the 4 forms, which is dt, dx, dy, dz. We had no problem at all with this one. Okay. The metric that we had here in the omega was for this specific example was a plus sign. So here also what we have a negative sign, but remember the metric is -1, so we are okay. Remember the metric is the determinant of this is -1. Okay. And what is happening with this one? We are going explicitly with the example of dt, dx, and dy and dz. So remember, the product of these four will together will be equal to -1. Okay, that's correct. And then if you do look at the conjugate of that, or the dual space of that, then definitely, since the metric is equal to -1, then I'm expecting that -1 appears here as well. It's not identical to the +1 in the calculation. If you go with the three forms instead, if you go with the dt, dy, and dx and dy, then if I'm looking for the dual of that, then the dual of the dt, dy, dx, dy will be equal to dz. First of all, the sequence is important because it should be t, x, and y. The sequence are important. And some people, they say that why we don't have a -1. I say that because here you have the positive sign and the metric is -1. So then that is already satisfied, and the result of this will be equal to plus dz. And in general, I can write it even dt, dxi, dxj. As soon as I and j, they go with a permutation, positive permutation, the dual of these will be equal to dk, dxk. No need for a minus sign. The same situation will appear also in other consequences, which is the going with the permutation of, let's say, dxi, dxj, dxk, which if you go with the star of dxi, dxj, dxk, the result of these definitely will be dt. Okay, in the same fashion. For the two forms, things get very complicated depending on whether you are dealing with the dt, or you're going with the even permutation or odd permutation. Then the result of these will be, I've written here, let me just find it out. Yes, if you go with the dxj, wedge product of dxk, then the dual of these will be dxj, dxk will be dt, wedge product of dj, dxj. And if you go with the dt, that will be the dt, wedge product of dxi, then that will require a minus sign. So dt, wedge product of dxi, that will be minus dxj, wedge product of dxk. So in a more general, you have to really count what is the location of that, and depending on the metric that you have a minus factor in a power of the p forms in your calculation. You can find that. I will send it as a note to everyone how to do this calculation for any arbitrary dimension. Okay. Thank you, Isa. Good. Lovely. This is important because when it comes to the Minkowski space, we have to do a little bit of the calculation in a different formalism. Okay. Good. Now I can go without having any problems, since I know how to do the algebra. Now I can go to do the differentials, which is the differentials is very important in the Grassmann algebra. So now is the differential of let's call it derivative of differentials. Derivative of differential forms. Okay, so now I'm introducing D. Okay, I'm introducing D, which means that I have to take the derivative of omega, which, remember, omega can be a P form. Is that clear? So now we are treating it like a new entity or new physical or mathematical entity, and we want to understand how to treat these in terms of taking its derivative or taking the integral of it. And you will see why I care about it, because it's so wonderful and includes all of those calculations that we previously learned. Okay, so I want to take the derivative of any, let's say, any P forms. So derivative of, let's call it the sum of the two, let's say, P forms. So assuming that omega is P form and omega prime is the P prime form. Okay, yes, probably we will get a higher orders, of course. So if P is equal to P prime, then I can take the derivative of the sum, and then it will be D omega plus D omega prime. Okay, that's the first result that I'm expecting. Remember, D, that is true, that is look like operator, but has the same meaning, is the differential, is the infinitely small displacement or variations in the quantity that you have. So for example, if D is acting on X, it will be dx. But remember, the dx is the differential form, and we have to take care when it comes to the Wedge product, or when it comes to finding the dual of it, and etc. So it has the same meaning with some constraint or rules that we have to follow. Okay, good. Now, F, I will introduce a new quantity, which is F, which I will call it the zero form. So F does not contain any derivative, does not contain any differentials. Okay, it look like, for example, the coefficients that we consider. Assuming that I have a differential form of F omega, which F is the zero form, and omega is P form, as we discussed. Now, how to do the differential of the df omega? So we are again following the same rule that we learned. It will be, the result of this will be the differential of the zero form. The differential of the zero form will give us one form. And then what we have the Wedge product of omega. Okay, because it's increasing, as Isa said, that is increasing the form to one order, and plus f d omega. Okay, exactly the same way that we were expecting. Good. That's the second rule that we have to learn, and is very, very important. So that's the first rule. That's the second rule. The third rule. The third rule is getting a little bit complicated. When you take the derivative of not the sum of the two, let's say, differential forms, but the product of two differential forms. How to do the derivative of omega Wedge product of omega prime, and assuming that omega and omega prime, now they are different forms. So one of them is a P form, the other one is a P prime form. So if you do, and that's an axiom, by the way, and the result of these will be d omega prime plus minus 1 p. P, remember, is the form of omega. Omega, which product of the omega prime. Okay. We will go through this in a few minutes, and I have to explain some part of it to you. Okay. Clear? The fourth rule is that the derivative of omega is equal to 0. They call these Poincare lemma, which is telling us about the analytical functions of omega, or analytical form of omega. Okay. And finally, remember, if you have, this is something that we got familiar with it. If you have a scalar, or a zero form, which is this zero form is a function of, let's say, x1 until, I don't know, xj or x p, then the derivative of f, which is the zero form, the derivative of these will be taking the derivative of f with respect to any of those x, then dxj. Remember, there is a summation here on j from 1 to p. So if you take the derivative of a zero form, then you will get the one form, and the element of these is given by that way. Yes, only the third one is an axiom. Okay. Good. So now with this, I should be able to take the derivatives of these differential forms, and you will see in a few minutes, which is why this is really, really important. So let's go with, remember these three. So is the derivative of the sum, derivative of zero form, and p form, which is what we are dealing, the derivative of the product of two p and p prime forms, derivative of a form, okay, and finally derivative of a scalar or a zero form. Okay, so these are the 5 rules that we have, and these are given in this sequence, and this axiom is based on of any previous experience. Well, no, this is based on what we call it, people, they call it antiderivative formula. Okay, this axiom comes from the being antiderivative, because you have these minus 1 power of p, because I will show it. I will show it to you in a few minutes. Questions? No questions? Okay. Well, now let's go from the last one. Okay, one of the last. D of omega is equal to 0. This is what we call the Poincare lemma. Okay. What it tells us about some specific function. Let's go with the simple, let's say two-dimensional space of R2, and assuming that I have a function, which is this function of x and y is given by this way, then I will create the one form of it. So it means that I will take the df. So the df will be equal to derivative of f with respect to x dx plus derivative of f with respect to y dy. Okay, this is the one form, essentially creating from a zero form, we create a one form. Now the other things that I can do, I can take the derivative of f, which f is a zero form, and the result of this will be equal to taking this derivative of f with respect to x of dx, f y dy, and taking the derivative of that essentially will result in derivative of x of derivative of f with respect to x. X, and that will be dx, wedge product of dx, because I'm taking the first derivative with respect to x. And then the second one, I will get the derivative with respect to y of f with respect to x, and then it will be dy, wedge product of dx. Then I have the second term, which will be derivative with respect to x of f of x, which is the dx wedge product of dy, plus derivative with respect to y of derivative of f with respect to y, dy, wedge dy. Okay, so what's going on with the first and last term? This and this term, they will be equal to 0, right? Because the wedge product is equal to 0. Lovely. This is what Isa said. But look at the second and the third term. I can swap these two together and I will get minus dx wedge dy. And the result of this is derivative with respect to x, derivative with respect to y. Sorry, this is y. Derivative with respect to y of f minus derivative with respect to y of derivative with respect to x of f of dx wedge dy. What is the result of this? This is the second derivative of f with respect to x and y minus second derivative of f derivative with respect to y or respect to x of wedge of dx dy, which is equal to 0 for analytical function of f. So for this analytical function of f, essentially you can get easily swapping the derivatives with respect to each other and the result will be identical. Okay. I'm looking at the result. Okay, so then this is equal to 0. So easily you will see that the Poincaré lemma is correct. Easily we can see it. It's not a proof, by the way. It's not a proof, but we can see that for the 0 form will give us that what is happening with the continuity of the function being analytical, and the result will be equal to 0. We can do this in other cases. For example, I can do it in the case of one form or case of two forms, and you will see some other new results which they are wonderful and amazing. Okay, now going to the axiom. I can go with the axiom. How many minutes do I have? I have half an hour. I would prefer well, axioms, you can just check it by yourself, just giving you a hint. So you can have a d of omega wedge product of omega prime, and remember omega is the p form and omega prime is the p prime form. Okay, so what does it mean? That I have to take the derivative of omega, which essentially in a general form can be given by a1 dx1 plus sorry, it can be given by a dx1 dx2 dx3 wedge product until you will get dxp, because omega is the p form, and then I have the other term, which is omega prime. I have to put a wedge product here, okay, of omega prime, which is b of dx1, wedge dx2, wedge dx3, until wedge of dxp. p prime. Okay. Now, well, what I can do, I can write it as a d of a and b. They are the zero forms, and then you will get a b, right? And then remember, a and b, they are function of x1 until xn, so you have to take the derivative of that. And then we have dx1 wedge dx2 wedge until wedge dxp, wedge product of dx1 dx2 wedge until dxp prime. Okay. And now you have to take is look like a scalar, and this is look like let's say p plus 1 form, so p plus p prime form, and you have to take the derivative of that, and essentially you will get the two results. The two results will be the derivative of a and b, wedge product of the result that you have it here, plus a b, the wedge product, or sorry, the d of the entire of these things, which the d of these will be equal to 0, because we just discussed about that from the Poincare lemma. Now, when it comes to this derivative, it will be the derivative of a and b. So it's two functions, two zero forms, and essentially the result of these will be derivative of a with respect to x. I have not I, then multiplied by dxi, and then I have a b, and then taking the derivative of the second function will be a derivative of b with respect to xi of dxi, which is required the wedge product with the rest, which is two functions inside. And if you do the mathematics easily, you will get the summation of derivative of a with respect to xi and b plus a derivative of b with respect to xi. Then you have dxi wedge product of the two terms of wedge. Okay, and if you expand this, you will get the identity that we discussed. It will be the derivative of omega wedge product of omega prime, and then when you want to take this dxi to the other term, then you have to go through the p forms that you have it here, and when you swap each of them together, you will get a -1, and then you have to swap it p times, and then you will get -1 power of p, and that's the reason that you will get -1 power of p, and then the result of these will be omega wedge product of the omega prime. Okay, I hope that is somehow, I went very quickly, but if you go through the calculation, it will be more clear to you. So that will be the result that I'm expecting. So now in the next half an hour, I will go through some of the usefulness of these this calculation. It's beautiful in many senses, and people, they will enjoy it. So again, remember that's a scalar product of f, which in general, the scalar product can be a function of x1, x2, and x3 until, I don't know, xn. And we already introduced what is happening with the derivative. So if you take the differential of the zero form, essentially, what you will get the derivative of f with respect to x1, dx1, derivative of f with respect to x2, dx2, and derivative of f with respect to xn, dxn. Okay. And well, indeed, this is nothing more than the first component of the gradient dx1, and that's a second component of the gradient of f dx2, and plus the n component of the gradient dxn. Okay, so we knew about that. Nothing is surprising here. I can take now I can take the derivative of the one form. So assuming that I have a one form of omega, let's go with, I mean, simply ax dx, ay dy, az dz. You can go with dz. And now I'm taking the derivative of omega. So what I have to do, this is the zero form, this is a zero form, this is a zero form, and that's a one form. So remember that we had a formula for f omega, how we have done the calculation. That was df Wedge product of omega plus f Wedge product of d omega. If you remember, that was what we added as a second term here. That was what we had. Okay. Remember, that was good. So, and now I have to do the calculation, and let's do the derivative of ax dx, ay dy, az dz, and derivative of the first one will be derivative of ax with respect to, I'm writing for full of them, okay, for the full derivative dx plus derivative of ax the dy az x z dz, which product of dx, I have only taken the derivative of this, okay? And then I have the second term, which is ax derivative of x, which we agreed that is equal to 0. This was coming from the Poincare lemma, okay? Then I have to take the derivative of the second term, which will be this one. The derivative of the second term will be plus derivative of ay x dx, ay y dy, ay z dz, which product of dy, and of course I have ay dy, which is again equal to 0, and then I have finally derivative of az x dx, derivative of az y dy, derivative of a z dz, wedge of dz. Now I have to expand it. So dx wedge dx will be equal to, I'm looking at the Q&A. Zero. Isa is correct. So the result of these will be equal to 0. dy dx, I have to keep it. dz dx, I have to keep it. This one also will be 0. This one also will be 0. Okay. So d omega then will be equal to, I'm writing the expansions. So it will be derivative of ax y dy dx from the first one. The second one will be the derivative of a x z dz wedge dx. That's coming from the first term. The second line, you will get derivative of y x dx wedge dy, and the last one will be derivative of ay z dz wedge dy. And finally, you will get the derivative of AZ x dx wedge dz plus derivative of AZ wedge dy wedge dz. Okay. Now we have to go with a positive permutation. So it means that I have to go with x, y, z. So I have to go with the sequence. So is y the x? So I have to swap them. Then I will get minus dx wedge dy. Then I will get minus dx wedge dz. What else? What else? X, y is correct. Z, y is negative. So it will be minus dy dz. Okay. And finally, x, z is okay. Y, z also is okay. So d omega will be equal to the result that I will be writing here. It will be derivative of AZ respect to y minus, I will go with the first one, and the upper one, which is derivative of AY Z dy wedge dz. Then the second term will be okay, the second term will be x and y, no, x and z. So derivative of z of x, derivative with respect to x of AZ, no, sorry, my apologies, x of z. Then I have the dx dz, and finally I have the last term, which is the last term. It should be dx dz dy. So it will be derivative of ay x minus derivative of x y of dx wedge dy. Good. So far, so good. Right, guys? So what is that? That's the curl of A, the x component, curl of A, y component, curl of A, the z component. So derivative of zero form will give you gradient. Derivative of the first form will give you the curl. Okay. Now let's go with derivative of the two forms. Let's see what it will be the result of the derivative of the two forms. So assuming that omega is a two form, which means that omega is given by the expansions that I have is B1 dy dz, B2 dz dx, B3 dx dz, dy, sorry. So these are the two forms. Do you agree, guys? These are one of the examples of the two forms. Questions? No question. Is that clear? Okay, perfect. So This is one of the two forms, and remember we are working in a three-dimensional space, is not n-dimensional space, else we have to have other terms as well that we have to take care. So that's in the three-dimensional space. And now I am doing the calculation and I want to calculate what is going on with the derivative of omega. So if we want to take the derivative of omega, remember B1, B2, and B3, these B1, B2, and B3, they are function of x, they are function of x, y, and z, okay? So if I want to take the derivative, it will be the derivative of B1 dy dz, okay? Derivative of B2 dz dx, derivative of B3 dx dy, and etc. And that's all. And you can expand this using the formula and using also the Poincaré lemma. Only the first term is important, so it means that you will get the derivative of B1 with respect to x dx, derivative of B1 with respect to y dy, derivative of B1 with respect to z dz, dz, and then Wedge product. Remember, it was d omega Wedge product of the omega, d of f omega. The result of this was df Wedge of omega plus the other term was f d omega. And remember here, since d of dy dz is equal to 0, that's the reason that I'm not writing that anymore. But the result of this will be dy dz, okay? And in the same way, I can write it for the other two terms, essentially. But let's just concentrate on the first one. If you do for the first one, yeah, I have to do expansions, dx expanding here, dy expanding here, but dz expanding on that one will be equal to 0, dy also will be equal to 0. So the result of these will be derivative of b1 with respect to x, and then you have a dx, dy, dz. Because dy dz is equal to 0, dz, dy, dz also is equal to 0 because they are repeated differentials. Okay. In the same way, you can prove that also for the other term, derivative of b2 with respect to y dy, Wedge dz dx will remain, and the last one will be the derivative of b3 with respect to z dz, Wedge dx, Wedge dy will remain. So x, y, and z, they are in the positive sequence, is perfect. Now let's swap these. It will be, let's swap the dx dz. It will be equal to -1, so it will be dy with the negative Wedge dx, Wedge dz. You swap these two together, you will get positive dx, Wedge dy, Wedge dz. So it's a positive sign. The same, if you do that, also you will get these two together, you will get minus dx, Wedge dz, Wedge dy. You will get swap them together, these two. You will get dx, Wedge dy, Wedge dz. Okay, and the result of that will be equal to derivative of b1 with respect to x, derivative of b2 with respect to y, derivative of b3 with respect to z, and then finally you will have dx, dy, dz. So the result of the derivative of the two forms is is a divergence. That's a divergence of b. Okay. So simplifying this, remember, in a three-dimensional space, as we say, zero form will give you gradient. If you take the derivative, it gives the gradient. One form, if you take the derivative, it gives you the curve. if you have a two form, take the derivative, it gives you the divergence. Okay. Now, as an exercise for you, because you will see now how beautiful is that. Derivative of a one form, zero form. What is the result? Should be zero, right? That's what we learn from Poincaré lemma. Derivative of f is equal to zero, right? Is Poincaré zero? Okay. Then, if you do the calculation, the result of this will be the gradient of f is equal to zero. It's so beautiful. Okay. Or the other one is going with let me see. I have done another one which was also very beautiful. Even if you do that for a two form, if you do it for the two forms, and the two forms should have a specific function, d of omega that I define is equal to zero. Then from here you will get the divergence of curl of A is equal to zero. And remember, omega, you have to write omega as A dx, AY dy, AZ dz. That's the beauty of, again, differential geometry. So I have 12 minutes, and yes, that's the beauty of mathematics, indeed. So that you can do a lot of calculation, and at the end you will simplify everything in a simple fashion. So in these next 10 minutes, what I will do, I will reuse these differential geometry, and I will write you Maxwell equations. Okay. Maxwell equations in this formalism can be written in this way. D of f is equal to zero. Okay, I will tell you what is f. But if you write in a differential form, this is the result. And the last one, of course, I know the result, but I want to be very precise. So is the differential of the star of f is equal to j. Now I will tell you what is the f and what is the j. Okay. Okay, so these are the two, or I call them Maxwell's equations. So what is f? Well, f, this is what we call it, this electromagnetic tensor. And remember, this is what we learn also from the special relativity. I mean, if you can look at some of the lectures that I had for electrodynamics and also for the quantum theory of light, I start usually for different formalism, something like first from the special relativity and going with the stress tensors, and or I can usually also try to introduce a new vector which is imaginary and real part of the that vector will give you the electric field and magnetic field. It is Riemann-Silberstein formalism. But anyway, going with stress tensors, so essentially electromagnetic stress tensor. And I remember I'm still working in natural units, which means that h bar is equal to 1 mu and epsilon is equal to 1, then c is equal to 1. So I'm looking in this unit, which again is just a matter of the choice. So the stress tensor that I introduce here is given by minus ex, okay, dt, which product of, did we use dt or did we use the x0? Which one did we use previously, if you recall? Because I need those equations. Can someone type and tell me? We use dt. Okay, so let's go with the dt, which product of dx minus ey dt, which product of dy minus ez dt, which product of dz. Okay, so these are the three electric fields component. And on the other side also I can write the magnetic field, but when you write the magnetic field you have to work with the space form. So it's plus bx dy dz plus by dz, which dx plus bz dx, which dy. Good. Remember, this is the stress tensor. And what is the form of the stress tensor? Is one form, zero form, two forms? Is a two form. Okay. Lovely. Now I'm asking you, what is happening with the differential of f equal to 0? Remember, this is not a rule. This is my condition for having a Maxwell equation. I'm telling you the differential of f is equal to 0. Okay. And well, before going there, what is going on with the dual of f or the star of f? What is the star of f? Again, it will be two forms. Again, you will expect that you will have 6 components. So the star of f will be ex. Now, using the same way that I introduced to you how to calculate the Hodge operator, essentially you will get minus ex. You will get dy, which dz. So this is the first one. Plus ey dz, which dx, plus ez dx, which dy. Okay, and finally the last term, which essentially will be bx dt, which dx, plus by dt, which dy, plus bz dt, which dz. Okay, so we also know what is going on with the star of f, okay, or the dual of the f, the stress tensor. So I will prove to you that, well, if you do the calculation and calculate what is going on with df, you will get this relation. So df, I'm taking the derivative of this one. Okay, let's do the calculation. So let's do the mathematics. It will be the derivative of minus ex dt, which dx, minus ey dt, which dy, minus ez dt, which dz, and of course plus d of bx dy, which dz, plus the other term. Let's just do that step by step. So again, using one of the formulas that we have, the derivative will act only on the first one, and the second one will be equal to 0, but you have to do the wedge product. So the first term will be, excuse me, minus derivative of EX with respect to, now is a function of X. Or maybe we have to go first with the T, dt. Ex function of time, x dx, ex y dy, ex z dz, and then we have the wedge product of dt wedge dx. Remember that I have just only written this term. Okay, this is what I have written for the first term. So since I have a dt and dx here, any wedge product that contains dt and dx will be equal to 0. So this term will not contribute. This term also will not contribute. So as a result, for this part of the calculation, I will get minus exy, then I will get dy wedge dt wedge dx, and then I have also the other term, which is minus derivative of ex z dz wedge dt wedge dx. So I got two terms from the first derivative of ex, and from the same way I can do the calculation, and I will write it just hopefully in a proper way. Derivative of y with respect to the time also not play a role, so it will be derivative of x of dx wedge product of dt wedge product of dy, and then I have minus the derivative of ey with respect to y is z of dz wedge product of dt wedge product of dy, and then I have minus the derivative of ez with respect to x dx wedge dt wedge dz, then minus derivative of y with respect to y. Oh, sorry, that should be z. Dy wedge dt wedge dz. Okay, so now I have taken the derivative of all the E component, and then I have to take the derivative of the B component. So the derivative of B component means that one. Okay, so I can also arrange them together. Maybe even before going to taking that derivative, I can even arrange them together. Let me see if we can do this kind of calculation that contains y, t, and x. So t, x, and y, t, x, and y, t, x, and y. Where we do have the t, x, and y, t, x, and y is that one. No, sorry, is this one, t, x, and y. Okay, so in order to get them the same, these two are different by a negative sign. Okay, I can arrange them together. So the result of these will be equal to so I have the three terms. Swapping t and x, I will get a positive sign. It will be derivative of ey with respect to x, and the other one, if I swap these two together, I will get a minus sign. I will swap these two together, I will get a minus sign. I will swap these today, I will get another minus sign. Getting minus ex y. Then I will get dt, which dx, which dy. That's the first one. I can do the same for z, t, and x. Z, t, and x, which is that one. I will get derivative of ez with respect to x minus derivative of ex with respect to z. Then I will get dt, which dx, which dz. Okay, I will get that one. And finally, the last term will be derivative with respect to z of y minus derivative of ey z. Then I have dt, which dy, which dz. Okay, so this all about the electric field. About the magnetic field part, which means that I have to take the derivative of the magnetic field, which is the derivative of bx dy, which dz, plus by dz, which dx, plus bz dx, which dy. I have to take the derivative of that. And if you take the derivative of that in a similar fashion, you have to do the entire calculation. You will get a result. I can type it down. No, God, what is it? Okay, I have that here. So the result of this, indeed, the result of this will be essentially given by the full df. The full derivative of f will be equal to, if I'm not mistaken, derivative of e with respect to y minus derivative of e y with respect to z minus derivative of magnetic field with respect to time. And then we have the dt, which dy, which dz, the first term that I have written on the upper side. Then I had the derivative of e with respect to x, derivative with respect to z minus derivative of z, ez with respect to x, plus the derivative of y with respect to time. Then we have the dt, dz, dx. Okay, and then I have another two terms which are very important. So I have a derivative of y with respect to ey with respect to x minus derivative of ex with respect to y, plus derivative of bz with respect to time. And then you have a dt, which product of dx, which product of dz, dy. And finally, I have another term, which is derivative of bx with respect to x, derivative of by with respect to y, plus derivative of bz with respect to z, of now is the coordinate term, which is dx, dy, and dz. So which is equal to 0. So it means that each of those terms should be equal to 0. And then from these two, from that one, you will get the divergence of b equal to 0. From the other three, you will get the curl of electric field plus derivative of b with respect to time should be equal to 0. So this is coming from the fact that if you have the stress tensor and you set it the derivative to be equal to 0, then you will get the two Maxwell equations to be satisfied, which is divergence of b is equal to 0 and the curl of E is equal to minus time derivative of magnetic induction. If you take this, the conjugate of F and taking the derivative equal to J, which J is what we call the 4 current, and J is equal to what we call it the well, let me write it in this way. The 4 current, essentially 4 currents are given by J mu, which is rho and Jx, Jy, and Jz. But also I have to introduce them in the proper way if you want to use them in the proper way of the forms. So J, it will be a 3 form, so it will be a rho dx dy dz plus Jx dt with the negative sign because the metric is negative. So dt dy dz, and then I have minus jy dt, which dz dx, and finally you have minus j z dt, which dx, which dy. And if you do that and doing the calculation from these two, you will get the other 2 terms of Maxwell equation. So the curl of a magnetic field is given by a magnetic induction will be J plus the derivative of electric field with respect to time, and then the divergence of the electric field is equal to rho. So you will get the other 2 terms. So well, forms are really forms are really powerful tools, and you will see that you can compact everything. And also you can write the Stokes theorem in a very easy way. So the entire Stokes and Gauss theorem will be given in a simple format. I don't have a time going through these, but essentially if you have an integral of a form, any form that you have it on a boundary of R, that will be given by integral of this integral of on the boundaries, essentially. So on boundary of the R. So you can look at the forms and you will see that these are really important, and that's a Stokes theorem. And you will see that the Gauss and all of those, they are already hidden inside of these calculation. So anyway, what I want to tell you guys that I mean, I hope that you learn some of the new mathematics, I mean, new definitions that we are dealing with, and we started from the calculus, but essentially we ended up with even new mathematics. So I hope that this course was useful for you guys. I'm sorry for going a little bit beyond the time, and for sure I will try to think about having the mathematical methods the second part of this course, which will be going through the group theory, special functions, and also complex analysis sometime soon, but I don't have any expectation at the moment. So thank you very much. I will stop the recording. I will stop also the live